In an endless, two-dimensional world, there are infinite airfields, distributed so that no two of them are at the same distance. At each airfield, a single plane is resting. When the signal comes, they all simultaneously take off and fly to the nearest neighboring airfield. After all planes have landed, what is the maximum number of planes that we can find at one single airfield? By now, you should start to be relatively familiar with the two sets of strategies, so let's jump straight to selecting the ones that we will be using. I would encourage you to pause the video here and think about it on your own, as by selecting the right strategies at the beginning, you will be pointed more easily to the solution. And as I said multiple times, don't worry if the first path you take is not bringing you anywhere. You can always try a different one. From the general set, I will include number 1 and 2 as usual, which are use the information contained in the text and develop an intuition. Maybe an element of number 3, symmetries, number 4, solve a simpler version of the problem, and number 6, draw a sketch, as we can kind of feel already that this is going to play a role here. I will, as a personal choice, also apply number 5, reformulating the problem in terms of points and distances rather than airfields and planes flying. But this is just because it helps me in my reasoning. From the technical ones, we can think of playing an adversarial game. This will help us in building a procedure to get to the solution. The difference here is that we're not playing against randomness. By saying that we have an infinite plane with an infinite number of airfields and asking the maximum number of planes that can land on one single airfield, we can actually think randomness playing to our favor, and what is playing against us are actually the rules and the constraints of the problem. As a little bonus, we can also look at number 7, learn a little bit of programming, but we'll get to that at the end of the video. Let's forget about an infinite number of airfields. This will just not help us, and let's focus on one, the one that will have the most planes landing on it at the end of the game. And as I said, I will think of it just as a point on a 2D surface, rather than an airfield, and I will call it C for center. Now we want to start placing points around, corresponding to the airfields from where the planes will take off and land in C. Let's apply strategy number 1. There is a clear constraint. No two airfields, or points, should be at the same distance. A way of understanding the role of this constraint is to deliberately violate it, see what happens, and then come back. Now strategy number 2. What is making this problem hard? Well, say I start to add points around C, and I will call them Ni. So N1 will be the first neighboring point, N2 the second, and so on. Soon I will start to have these Ni points at a relative distance that is shorter than their distance to C, so that the plane would not land on C anymore, but rather on some other Ni. So we need to keep in mind that any time we add a neighboring point, we have to make sure that its distance to any other Ni is larger than the distance to C. This somehow suggests a way forward. Let's start from C, and because of symmetry, telling us that there is no specific scale or orientation which is intrinsically different from any other, we can place the first point where we want. So I will just place it here. So let's now try and add a second point, N2, keeping in mind this crucial aspect. Its distance to N1 should be larger than its distance to C, but in addition, its distance to N1 should also be larger than the distance from N1 to C. Otherwise, the plane taking off at N1 would land in N2 instead of C. The first definition implies that N2 should lie on the portion of plane to the left of this line, dividing points closer to C or to N1. The second requires N2 to lie outside this circle. The intersection is an interesting point, as this would mean that the 3 points are all at the same relative distance, violating the constraint of the problem. But for now, let's accept this and place N2 exactly at the intersection. We will come back and fix it later. We can now repeat the same construction a few times, and each time we add a point. How long this goes on before we get back to a starting point? Now, depending on your geometry skills, you can find the answer in a few different ways. 1, the easiest. You make a very precise drawing, and you will see that after 6 points, your 7th will overlap to the first. 2, you might have realized that the first 3 points are forming an equilateral triangle whose angles are 60 degrees, and you need 6 of them to go around the full 360. 3, you might know that a hexagon inscribed in a circle has edges equal to the radius of the circle. No matter how, the main point is to get to this construction, where we have 6 neighboring points, all at the same distance to C, which I will call D, and such that each of them is a distance D to 2 other neighboring points. This is a moment when we have to go back and enforce the constraint we deliberately violated until now. Starting from N2, we have to make sure that it lies not on the circumference or on the line, but outside the shaded area, even by an infinitesimal amount. And when we build the same construction from N2, N3 should lie outside the new shaded area generated. So it will have to be an infinitesimal amount further, and so on. Although this is a very small change, crucially, after we placed 5 points, it makes the 6th point end up inside the shaded area generated by the first point. So, summing up, we can get up to 5 points, but we can't have 6, as this would violate the constraint of the problem. Did you solve it? Was it harder than the other riddles we looked at? Let me know in the comments down below. What we showed is that the theoretical maximum number of planes to reach one airfield is 5, but this says nothing about how likely this is. To check this, and also as an excuse to look at how we can use programming to help us out, let's write a little Python code to simulate what is going on. So we will need to import some math function from NumPy, so import NumPy, and maybe also matplotlib, as we might want to draw some scatter plots. Now we can't program an infinite number of airfields, so let's set a number, n, let's say it's 500, but we can always come back and increase it. And each airfield can be represented by a random point with 2 coordinates, x and y. So let's use random to generate such arrays. So airfields is equal to np.random.random with a shape of n rows corresponding to n airfields and 2 columns representing the 2 coordinates. Now, just to make things a little bit easier in terms of names, we will call airfields x the first coordinate and airfields y the second coordinate. So now we need to define a function that for a given airfield checks where the plane taking off from that airfield is going to land. So let's call this argmin_dist for argument of minimum distance. And this is a function of an airfield A. So we can calculate the distance from A to all other points using the Pythagorean theorem. So we can compute distance is equal to the square root of the square of the difference of the x component plus the square of the difference of the second component. Okay, now we need to consider that the closest point to A will be A itself with a distance of 0. So an easy trick is to set this distance, so distance corresponding to the argmin of distance, which we know it's A itself and the distance is 0, we'll just set it to 100. So that when now we recompute the same thing, we will have the actual closest airfield, and we can call this am_dist. And now the function just has to return am_dist. Okay, so all we have to do now is to initialize a list of destinations. And then we'll run a for loop for each airfield, and we will just append to this list the result of running the function on this airfield. Okay, finally, the last thing we have to do is to print the maximum number of planes landing on a given airfield. So one way of doing this is by taking the destination as a set, and then we can take the maximum using the key dest.count. So what this will return is the element that appears most times in the list. And now we can just do dest.count how many times this element appears, and we can just print this. So we can now run the code in interactive mode, and we can see that we get 4. So we have a single airfield with 4 planes landing onto it. But now we can just go back and increase n to simulate a more realistic scenario. It turns out it is very unlikely to have 5 planes landing on the same airfield. I ran the script with n equal to 1 million, and still I could only get as high as 4. How many airfields do you actually need to get to 5? If you try and succeed, again, let me know in the comments. If you enjoyed this video, make sure you press the like button and subscribe to the channel to get notified when our next riddle is out. I will see you in the next video. I am Yuri, and this is RiddleBear, the channel that will help you develop riddle solving skills and be able to solve riddles you didn't think you were capable of.